A very good afternoon to all IEM UEM family member. Today, Professor Debarghya Dutta, Assistant Professor of Electrical Engineering Department, UEM Jaipur, will be discussing a very important, very interesting topic on Fibretronics, which is actually a technique for combining computing devices with fabric, clothes, and other soft, flexible material. I hope the session will be of very good interest for all of us. So over to you, Debarghya sir. You kindly take over, please.
Thank you, sir. So good afternoon, good evening to my dear colleagues, teachers of IEM family. And my name is Debarghya Dutta. I am an assistant professor in Electrical Engineering Department, UEM Jaipur. So welcome to today's webinar on Fibretronics. So I have divided my talk in three different sections. So in the first section, we'll discuss about Fibretronics. We'll get some insights about Fibretronics. Then in the second section, we'll study some electrical design using sensors and transducers, followed by testing and fabrication. So these are the three essential sections. So in general, so what is Fibretronics? So the science by which we combine a fiber and electronic component in a fabric, that is known as Fibretronics. So Fibretronics is essentially fiber plus electronics. So it's a generic term, but we'll see by the end of this session that how Fibretronics is related to AI, ML, and DL. So let me give you one example. For example, I'm wearing this t-shirt. So this t-shirt is made up of several non-conductive fibers or non-conductive yarns which cannot conduct electricity. But the advantage of this thing is it is flexible. So we can bend it, we can do in whatever shape we want, but it cannot conduct electricity. But let's say if we want to integrate or embed an electronic component or electrical device into this shirt, then what is the best possible way? So the best possible way is that we can use specialized fibers which are designed for this Fibretronics specialization. Like we have conductive fibers and non-conductive fibers. So these are non-conductive fibers, and conductive fibers means fibers which can conduct electricity. So let us move ahead. So the combination of electrical circuits with a particular computational functionality is known as Fibretronics. So essentially these two things can be integrated into fabrics for various applications. So this Fibretronics, this branch is a subset of electronic textiles. Now what is electronics textiles? So textiles is very simple. The textile materials, the fabrics that we are wearing on day-to-day basis, these are non-conductive in nature, and these are very soothing, these are very comfortable to us, so that we can wear it on a daily basis, and which is under a set of wearable technology. So this is a very broad term. Wearable technology means something that you can wear, and alongside with this, you will have your mobile phone, you will have your chips, you can connect the Wi-Fi, you can connect the GPS with your fabric itself. So this whole thing will come under wearable technology. And under this section, we have electronic textiles, in which we can embed computational functionalities. So that is why it is more intelligent. So electronic textiles is much more intelligent than smart textile. And at the end, we have got Fibretronics. So this is a very specialized branch. It is a culmination of electrical engineering and lot of computational functionalities that we'll see during this session. So let us first try to understand what are the applications. I mean, why do we need wearable technology? There must be some reason for this particular specialization. So there are many applications of wearable technology. So it is used worldwide in military and emergency services. So these are the topmost priority, as you can see in this picture. So it's used in military and emergency services, in civilian purposes, then for the firefighters, where you can see that this person is wearing this jacket with all these electronic components embedded inside it. But as of now, it's a very heavy jacket. So only you can wear it when you need it. Otherwise, we cannot wear this kind of jacket, because from this picture, it is evident that we can carry these electronics components within this jacket, but if we do that, it will be very much bulky, so it is not so user friendly and it is not so comfortable. So this is a part of smart textile. This is a part of smart textile. This is not Fibretronics. Smart textile is something like you have got a textile fabric and you are attaching one by one component, one for GPS communication, one for Wi-Fi communication, one for mobile communication, one for health monitoring, and we are connecting all the devices together. And when we need it, then only we are connecting it. Once our job is done, we'll simply take it off. So this is the whole idea of smart fabrics or smart textile. But the difference between smart textile and Fibretronics or electronic textile is that in electronic textile we can connect, we can embed the electrical and or electronics devices using specialized wires or fibers. So these are for emergency services, and also we are using these things in healthcare and health monitoring on a real-time basis. And other than that, we have seen these things in televisions, like in innovative fashions we have seen. Sportswear, Adidas is one such company which is making a lot of t-shirts which has got a lot of sensors inside it, so that it can enhance the performance of the players. It can take real-time data from the players who are in the field. Like for example, in the year of in this year 2021, in the IPL that was scheduled on just a few months back, you might have noticed that the players are wearing a particular type of shoes which is given by Adidas and Nike. So it looks pink in color. It's quite attractive from aesthetic point of view. It's very good, but it's not a normal shoe that we wear. It's a functional shoe. So it's actually a performance enhancing accessories. Like in IPL, the players have to run very fast. They have to sprint. So for sprinting purposes, we are using this kind of shoes, which are specially customized shoes. So this is a part of smart fabrics, and altogether this is a part of wearable technology as well. As we can see from this stacked bar graph, that during this year, around 2014 to 2017, this smart textile market was globally mostly dominated by US and Canada, because they are having high disposable income. So high disposable income means you are having more money so that you can spend more money. So essentially they spend more money on the defense, the US and Canada. So during these years, we can see that they are mostly the dominant players. But around this 2021, as we can see, some other regions also, including India and the Middle Eastern countries, Asian countries, they are gradually developing these things on a large scale basis. And this is the projection that has been given for this 10 years. This is the forecast. So it's a broad market, it's commercially available, and we can do a lot of stuff. People are doing a lot of stuff in these things. So let's move ahead. And as we can see, so we have got natural fibers, which was at the very beginning. So cotton fibers, hemp fibers, woolen fibers, these are all natural fibers. It is available naturally. We don't have to manufacture it essentially. And from natural fibers came the chemical fibers. So people, what they did, they simply manipulated the molecular structures of natural fibers. So using nanoparticles, using some conductive particles made up of gold, silver, copper, aluminum. So they have injected all these things in the molecular level. And from natural fiber, we went to chemical fiber like polyester fiber. This is not a natural fiber. This is a non-conducting fabric, non-conducting fiber. And you might know this polyester fiber, mostly sports persons, they wear during their on-field performance, because you cannot wear a polyester fiber and go to sleep because it is not comfortable. It is manually designed. So it is a functional fiber, this chemical fibers or polyester fibers. We can say that it is man-made fiber. Then came the functional fibers, like optical fibers. So what is the functional fibers? So basic function is to integrate this into using Fibretronics. So from there on, we are getting into Fibretronics. So up to this, we are dealing with natural fibers, non-conducting fibers, and from functional fibers, we'll be dealing with conductive fibers, and altogether, this is the part that will encompass Fibretronics as a whole. So optical fibers, like if we want very fast communication using light waves, then we'll use optical fibers. And optical fibers, we can use optical fibers in our Fibretronics to design certain devices, because optical fibers, you can bend it, you can stretch it, it is very flexible, it is very hard, less loss, less interference, and less noise, very fast, and bandwidth is very high in case of optical fibers. But in terms of cost, it's a little bit costly, so we have to keep in mind the cost benefit ratio as well. Next, we have got conductive fibers. Conductive fibers are nothing but it's a specialized fiber which can conduct electricity. So essentially, as we know that in electrical cores, in the wires that we use in electrical engineering, so there is a core part and there is a covering part. So in conductive fibers also we have a core part, which is a non-conducting core, and on top of that there is a coating of conductive material. This can be either of gold, if you can, if it's costly, although it's costly, but its covering is gold or silver, or we can use copper, or all the conductive materials we can coat over it. So this is essentially conductive fibers. Then we have got antibacterial fibers, like due to COVID-19, this antibacterial fiber is of great use. So this antibacterial fibers is essentially used when there is a scenario of water molecules interacting with microbes. So as we know, if we wear a mask, so there is a high chance of interaction of water molecules from our mouth along with the microbes or virus. So during that application, we use antibacterial fiber, which most of the pharmaceutical companies, they are designing this mask using these fibers. Then we have got smart fibers, which we can use for energy harvesting. Because why energy harvesting is needed? Because essentially, if we are doing Fibretronics, then we'll carry all the components within ourselves. Like we'll have a GPS connected somewhere, some patch antenna connected somewhere, some mobile communication device connected somewhere. But for operation of that, we need one particular battery to supply current. But that is not possible, because if we connect a battery, then that garment will be bulky. So what we do, how to harvest the energy? We can harvest the energy from our movement. So this mechanical energy to kinetic energy to electrical energy. So like if we want to make a capacitive resistance, capacitive pressure sensor, or we can design resistive sensor using various combinations of our body movements. So this is one aspect of this. By this, we can harvest the energy from our body itself. I've listed some of the advantages, like advantages. What are the advantages of this? Definitely, it is very lightweight. These Fibretronics materials, it's very lightweight. It's durable. It's washable, because these are the generic advantages that we encounter. It's breathable, means even if you sweat inside, but you will not feel any discomfort, because the garment will take care of this. Then real-time tracking, if we have some kind of communication device that is already in our body, then we can track somebody, we can monitor the patients. Then this is for security authentication also. We can use this. Simply if I connect a RFID tag, it will act as a security authentication. And of course, it's integrable with human body. So these are the advantages of this Fibretronics specialization. And from theoretical point of view, it looks good. All these things looks good, but practically there are some disadvantages, like its reliability is very less. Then we cannot produce this on a mass scale, because till now this is on a research scale, and in developed countries they are doing this for defense purposes, for emergency purposes, but for general consumption of public, it's still not in use. Then we have limited processing and storage capability. That is another disadvantage. Limited flexibility. It's very simple. If you connect a lot of things in your fabric, obviously its flexibility has to be compromised. Bulky. If you don't make it flexible, obviously it will be bulky. So this is the main gap. This is the main research gap. How to reduce this bulkiness of these Fibretronic garments. Expensive. Yes, it's expensive, because we need to fabricate it also. There is a lot of testing behind this. So once we test it and we approve it, then we can design it. And privacy issues, obviously, like if you are wearing, like if we are monitoring a patient and we are collecting real-time heartbeat, then SpO2 level, then hemoglobin level, and everything, if you are connecting from a particular person, then obviously that person's privacy is getting in question. So privacy issues is there, and limited user comfort, because once you wear it, it looks good from outside, but from inside it is not that uh, comfortable. But the challenge is to make it comfortable. So that this is where we'll use Fibretronics. Now for intelligent textiles, like intelligent textiles, we can communicate either by any of these 4 parameters. Like we can communicate within our suit, like we have one communication device here, we have one communication device here. So either it can happen from this side to this side, or it can happen from this device to the person who is wearing it. It can transmit data, or it can receive data, or also this garment can transmit data from outside, from somebody else. So how it can be done using Fibretronics? So essentially there are two ways. One is optical fibers, as I've said, as I've mentioned in the previous slides. We can use optical fibers, and we can use conductive yarns or conductive threads. This is like a simple electrical wire, but its cross section is very less, its size is less, it's very lightweight. So it is similar to an electrical wire. So as of now, we have discussed about the brief introduction of Fibretronics. Now let us come to the electrical design considerations, like how we can use electrical engineering design and how we can use the electrical parameters to design these things so that we can fabricate these things afterwards. So this is an electromagnetic transducer. So what is a transducer? A transducer is a device, electrical device, in which you apply a alternating signal at the input and you get another signal at the output. So you apply one kind of energy at the input and you get another energy at the output. So in electromagnetic transducer, it means that in this kind of transducer, we'll apply a sinusoidal voltage source or a sinusoidal curve or a sinusoidal signal at one point, and at the other point we'll get electromagnetic waves. That is why this kind of transducer are known as electromagnetic transducer. One example of this is a patch antenna. So this is one kind of electromagnetic transducers we are all using in electrical engineering, these things. So this is essentially a patch antenna. So let me give you a brief introduction about these things without getting into the depth of these things. So this patch antenna has got this part. So essentially we have a ground plane. So what is the basic purpose? We have a fabric here. So let's say this is the fabric, which is non-conducting, and on top of that we'll place a ground plane. So the function of ground plane is similar to reference voltage that we take in electrical circuits. Like in electrical circuits, we consider the earth surface to be zero potential and we take it as a reference. So similarly, in electromagnetic transducer also, we'll take this ground plane as a reference voltage. So its function is only to reflect the radio waves and to complete the circuit, to complete the electrical circuit. So on top of the fabric, we have a ground plane, and on top of this ground plane, we'll use a dielectric or dielectric. So what is a dielectric? So dielectric is a material which allows you to store electrical energy. So less amount of dielectric, if the value of dielectric is less, you can store more and more of electric field in it. So you have this fabric, on top of that you are having ground plane, on top of this you are having a dielectric medium of height h, and on top of that you are having a patch that we call as microstrip patch antenna. So this is the patch that we are having here of length L and width W, and we are feeding this patch using a microstrip transmission line. So essentially this is the circuit diagram, this is the block, this is the diagram of a microstrip patch antenna. So in our case, in Fibretronics, we'll use ground plane by making it fully conductive sheet. So there are a lot of conductive sheets available, fully made up of copper. Generally we use copper. So in that case we can use copper because it is flexible, it is already available, it's flexible, you can bend it, you can wash it, you can do whatever you like with it, but it will act as a ground plane, that this copper plate. Then we'll use dielectric. Now the selection of this dielectric is very, very important in this case, because your transmission will essentially depend on the dielectric that you select here. Because if you select less amount of dielectric, or permittivity if it is less, then your transmission will be more. You can hold more and more of energy. So this is a very important parameter, this dielectric. So in normal case, in normal design for electrical engineering, we use Duroid or Taylor and all these things. Bakelite we use as a dielectric in normal design in our cases. But in Fibretronics, we'll use such kind of materials which are flexible and which meets this dielectric parameters. Like for example, if you wear a denim jeans, so that denim jeans has got a dielectric constant which is very favorable for designing this kind of electromagnetic transducers. So this is just an example I have taken. There are a lot of electromagnetic transducers like this that we use in electrical engineering. Like we have bow tie antenna, we have horn antenna, Yagi antenna, and all these things we have got. And this is the patch, and we are feeding this with the help of a microstrip line. So this is the whole thing. So here W is patch width, L is patch length, H is the height of the dielectric, and this epsilon r is the dielectric constant, and F is the operating frequency. Now if somebody asks you, how do you make an antenna, how do you design an antenna, so the first parameter that you should say is operating frequency. So this is the most important part. So as we know from our theory, from our books, from our basic literature, that we can design an antenna based on its length and width. And if you want to design this electromagnetic transducer using width, so this is the formula that we have got, C upon 2W, and this is 2 upon epsilon r plus 1. So this is the formula if you are using W, and this is the formula if you are designing this with the help of length. So either of these two you can use. So this is our operating frequency. Now operating frequency will depend on the application that you select, whether you want to operate this in 2.4 gigahertz or 1.9 gigahertz or megahertz. That depends on the application that you want to consider. So this is our electromagnetic transducer, and the dielectric that we'll be using here, that we can use here, has to be flexible so that we can bend it, we can do whatever we like with it. Because essentially when this thing will be in our garment, so obviously it will be subjected to wear and tear and stress, okay, every time. So this dielectric has to be flexible, so we can use many dielectric materials which has very good properties. This is one point. And this dielectric, including this ground plane, will be our circuit board. This can be our circuit board. Now as we know, our deep learning model works very well if we provide a solid number of training data. Our deep learning model will work very, very well if we provide right set of training data. Once we provide right set of training data, once we give this training data to some machine learning algorithms, and if it can give us some very good mathematical model, then if we apply this whole thing in this deep neural network, then we can expect that we'll get some optimized output, provided if we give this input values. So essentially in this case, our input parameters will be this one: W, L, H, epsilon r, and Fc, that is operating frequency. So essentially these are our inputs, and in the output we expect that it will give us some optimized better result. So this is done. Now the main problem is where we will get this training data from. And as we know, our machine learning algorithms works very well. It gives us mathematical model based on some training data that we provide to the computer, and alongside we'll provide some input data as well. So we'll test it, we'll train it, then we'll test it. So in that case, our machine learning algorithm essentially gives us mathematical model which we can study, and if we apply this mathematical model in deep learning, then we can expect very good output results. but the main problem in this case is this training data. So where we are going to get this training data from? Now, as we can see, these are all level data. These are all level data. We know every value and what is the impact of these values, we know. So these are all level data. So once we get this level data, so what we can do, we can go to CST Microwave Studio, or we can go to HFSS, which are nothing but electromagnetic environments, where we can design a lot of electromagnetic transducers on various frequencies based on our choices. And these are all EM environment. So it's a basically three-dimensional view that you have to construct a geometry. So this, every time you simulate a electromagnetic transducer in your CST or HFSS environment, so that data is going to be your training data. Like if you simulate this particular transducer 50 times using 50 different values of these things, this 50 data set is going to be your training data. I mean, you can differentiate it, training data, testing data, but whatever simulation you are doing using CST and HFSS for designing the geometry of this antenna or designing the geometry of this transducer, so that set is going to be your training data. So this is very important. So essentially we apply all these things in electrical engineering. We are applying machine learning algorithms and including deep learning network as well. So essentially, I hope this is clear. This is in very short. Like we have this level data, then obviously we can use supervised machine learnings. And in these cases, it has been seen that the you can apply a lot of like genetic algorithms you can use, which works very well in that case. Then regression based models also works quite well in this kind of electrical design. These are some of the references that I have given, like based on the choice of frequency, you can choose your material with particular height and dielectric constant that is given here. And we have another important parameter is tan theta. It is nothing but dielectric loss coefficient. It is similar to power factor, like in electrical, like we are using P equal to VI cos phi. So cos phi is essentially the power factor that has a huge impact on the end user. So this tan phi, this tan del is acting like a power factor in this case. It is just an analogy. So you can see this table and you can choose your material. People are using this kind of applications like 2.4 gigahertz. It is 2.45 is essentially used for Bluetooth, then Wi-Fi, microwave oven, then all these things. And the design procedure I have just shown in the previous slide. So the performance is written here, which one is good, which was unacceptable. So this is a generic overview. Now testing and fabrication. So the main challenge is to make it conducting. Obviously fabric should be conducting. So if we inject some nanoparticles, or if we take some copper or say aluminum or gold or silver based fibers, they are all conducting. Then circuit should be flexible. Obviously, if we are designing an transducer, electrical transducer on a flexible substrate, it should be flexible. It should be durable. We should have comfort also, ease of fabrication. This is very important. And all these things, all these Fibretronic things, essentially is in line with Industry 4.0 and also Industry 5.0, which I haven't mentioned here, because Industry 5.0 is essentially you are working with a robot. So you have designed something and both of you are working together. So that is IR5. So essentially you are doing this also. This is very much valid here in this case. These are conductive fibers which have a non-conducting core and a coating of conductive material from the outside with high conductivity. This is conductive fibers. We can use optical fibers. This is a conductive fabric. If you can stretch it, you will get a resistance. So based on your choice, you can apply all these things. Like you will get a resistance, then you can connect all this conductive fibers with this conductive fabrics to make it fully flexible. We can use conductive inks, like just simple, it's like a pen, or we have conductive adhesives, epoxy, glue, and gel, which we can use for interconnecting points, for joining the points. conductive ink screen printing technology is also there, but it's quite costly because this printer is not available everywhere. So it's available, but we have to make this design, and we have to purchase this ink, or we have to uh, keep these inks in proper way so that we can get our desired design. So this picture that you see, so from this reference, so this is essentially a electromagnetic transducer, and this is the feeding point, and this electromagnetic transducer has been designed using this conductive ink. It is fully conductive ink. We can do mesh analysis, like we have done mesh analysis in circuit theory using resistors, and capacitors and all electronic passive components. So similarly, this is just an example. Like this white portion is the non-conductive fabric or non-conducting wires, and this black one is conducting. So there are various types by which we can design this. One is warping method, one is woven method, like the shirt that I'm wearing is woven, and the sweater that you wear during winters, that is knitted. Then embroidery is also there. There are various techniques by which we can design this, and we can see. And for this, like once we make this electrical transducer here, we have to feed it using a connector, or in generally we use SMA connectors, because essentially what is the objective? We want to feed this point using an alternating source, and this portion will emit radio waves. That is our target, and this portion has to be connected to a frequency or spectrum analyzer. Then so this point is very important, because as of now this is, as it looks like, as if it is a very rigid device. This golden color, this SMA connector is rigid. It's actually rigid, but our target is to make it flexible. So we can use these things, conductive epoxy. It's almost like conductive adhesive, but essentially it doesn't work. Sometimes it works, sometimes it won't work. But we have got snap-on buttons, butterfly clasp, wing solution, and out of this wing solution is the best. It works well, very well. But there is no hard and fast rule using these things. So we have to apply trial and error method while connecting this, because you don't find this essentially everywhere, because we have to design it, we have to think it, we have to trial it, and then we can fabricate it. Like this, we can make a capacitive pressure sensor. Like for making a capacitor, we essentially need two plates. One plate should be positive, another should be negative, and we'll have a dielectric medium in between. So in case of Fibretronics, while designing electrical capacitive pressure sensors, we'll have a conductive fabric on one hand, and we'll have conductive fabric on another hand. Then we'll use a dielectric medium, also a fabric, and that is essentially our capacitive pressure sensor. We'll apply pressure and we'll get the output voltage. Similarly, we can have resistive pressure sensors. Like we have a conductive fabric, so you can stretch it. So once you stretch it, once you change its dimension, its resistance is going to change as per the formula, R equals to rho L upon A. And so once you change its dimension, its resistance is going to change. So like this, we can make a lot of electrical transducer sensors using simple fabrics. And this whole thing was just to give you a little bit of generic idea about Fibretronics and how electrical engineering, how we are using a lot of computational functionalities along with artificial intelligence, deep learning, and machine learning to make a better future. So that's it for today. So thank you everyone for attending this session. Thank you.
So Professor Debarghya, should I shoot the poll?
Yes, sir.
Okay. The poll is already there. I request all members to kindly start giving answers. The question is regarding the difference between part A, electronic textiles, and B, smart textiles. Which statement is most accurate? is more intelligent, 2 times, can be connected to a smartphone, both are same. So already 45 seconds and 45% voted. So has crossed 50%, reaching to, I think, 55% now. So I'm now closing it. So Professor Debarghya, I'm sharing the result.
Okay, sir.
So you can see here is more intelligent, 32% again is more intelligent. The second part is 23%, can be connected to a smartphone is 16%, and both are same as 29%. So what is your comment on this?
So, sir, the correct answer is A is much more intelligent than B, because as I have mentioned in the beginning, smart fabrics or smart textiles is something that, like an analogy I can give, like the flight pillow that we use. Like we use the flight pillow to sleep when we need it. Once our job is done, we simply take it off and disconnect it. So this is nothing but the essence of smart fabric. This is just an example. And in case of intelligent or electronic textiles, we can use computational functionalities so that it is much more intelligent than smart fabrics. So A is the correct option.
So actually in A part it is written is more intelligent only, and in B part also is more intelligent. So in your view, A part must be is much more intelligent, right?
Much more intelligent. Yes, exactly.
Okay. 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 So I'm hiding this result, and I'll try to see if any question is there. So few comments are there already in the question panel. I'll request the members to post the questions if they have any. I'm not finding any question yet. The comments is there from Madhusudan Daidya. Thank you, sir, for nice presentation. From Ankit Kumar Sharma also, very nice presentation, sir. Sanjay Mandal, nice presentation. So a lot of comments are there, Debarghya sir. So no other questions are there. I'll request again, we can wait for one more minute if any member wants to ask something. So kindly write in the question panel. Okay, I'm not seeing any question now. So thank you, Debarghya sir, for very interesting information-based discussion. Thank you. Thank you all IEM UEM family member. Thanks a lot.
Thank you, sir.
Good night.
Thank you.